To support the production of more high-quality content, consider supporting us on Patreon or YouTube membership. Additionally, consider visiting our parent company EarthOne for sustainable living made simple. Deep learning is a subfield of AI that has taken the world by storm, in large part since the start of this decade. In the 6th video in our artificial intelligence series, and as for the purpose of this deep learning series, we'll explore why it has exploded in popularity, how deep learning systems work, and their future applications. So sit back, relax, and join me on an exploration into the field of deep learning. As I hope I've gotten across in past videos in this AI series, artificial intelligence refers to any model that can mimic, develop, or demonstrate human thinking, perception, or actions. In the case of AI that we all refer to today, it is about computational intelligence, that being intelligence demonstrated by computing technology. Machine learning then is the ability for computers to learn without being explicitly programmed. In other words, having the ability to derive structure from data, that being the features of a dataset, to be able to predict future outputs, whether that output be a value or a category. We discussed both supervised and unsupervised learning techniques quite in depth in our machine learning series, and going a step further also discussed the 5 tribes of machine learning, highlighting the different thought philosophies and giving computers learning capabilities. Over the past few years, the rise in artificial intelligence and mainstream popularity has been attributed to the successes of the connectionist tribe of machine learning, spawning a new field, deep learning. The goal of connectionism is to digitally re-engineer the brain and all of its connections. The title given to this digital reconstruction of the connections in a brain is a neural network. Deep learning then is the ability to learn the underlying features in a dataset using neural networks. By this meaning, the ability to learn features directly from data rather than being hand-engineered. As quoted from a seminal paper on deep learning from the godfathers of the deep learning revolution, Geoffrey Hinton, Yoshua Bengio, and Yanli Kun, conventional machine learning techniques were limited in their ability to process natural data in their raw form. For decades, constructing a pattern recognition or machine learning system required careful engineering and considerable domain expertise to design a feature extractor that transformed the raw data, such as the pixel value of an image, into a suitable internal representation or feature vector from which the learning subsystem, often a classifier, could detect or classify patterns in the input. Representation learning is a set of methods that allows a machine to be fed with raw data and to automatically discover the representations needed for detection or classification. Deep learning methods are representation learning methods with multiple levels of representation, obtained by composing simple but nonlinear modules that each transform the representation at one level, starting with the raw input, and to a representation at a higher, slightly more abstract level. With the composition of enough such transformations, very complex functions can be learned. For classification tasks, higher layers of representation amplify aspects of the input that are important for discrimination and suppress irrelevant variations. Let's now take this definition of representation-based learning and apply it to an example, say of a neural net detecting a face in an input image. First off, this image is actually composed of an array of pixel values as the input to our system. Following that, the first few layers of representation learn low-level features, like the presence or absence of lines and edges at particular orientations and locations in the image. The next layers of representation begin discerning mid-level features based off the low-level features previously found. This involves finding particular arrangements of edges and lines and producing features like eyes, noses, and ears. Finally, the last layers of representation discover high-level features, that being a combination of mid-level features to identify different facial structures. The key aspect of deep learning is that these layers of features are not chosen by human engineers. They are learned from data using a type of general-purpose learning procedure. This as opposed to the hand-engineered features of traditional machine learning algorithms, which is time-consuming, costly, and overall not scalable for more complex applications. The true birth of deep learning, that being when the mainstream got wind of it, and where an algorithm publicly demonstrated this feature detection capability, came back in 2012 at the ImageNet competition. Since 2010, the annual ImageNet Large-Scale Visual Recognition Challenge is a competition where research teams evaluate their algorithms on image datasets. These image datasets are comprised of millions of images in approximately 1,000 image categories. Along with a variety of changing completion milestones, the general year-to-year goal is to get as low as a possible error rate in the classification of images in the dataset. In 2010, the inception of the challenge, the error rate was 28%. Progressing forward, in 2011, this error rate for the winning team dropped to 26%. However, as you can see, there was quite a bit of spread in between the teams. In 2012, most teams began converging around the 25 to 30% range in error rate through the use of traditional image recognition, in other words classification machine learning algorithms, like those we discussed in our machine learning series. There was one major outlier in 2012, however, the winner, an algorithm dubbed Supervision, with an error rate of 16%, nearly 10% better than its closest competitor. Supervision, more academically referred to as AlexNet, is a deep convolutional neural network with 8 layers, terms we will dissect later in the series. It was a network designed by University of Toronto professor Geoffrey Hinton and his graduate students. By the next year, 2013, nearly every top 5 team had switched to a deep learning approach, with the winning team having an error rate of 12% and 8 layers. Progressing forward, in 2014, the winner had 22 layers and an error rate of 7%. And by the next year, it was the first time that the human record error rate on the dataset of 4.94% was breached by a network, dubbed ResNet, comprised of 152 layers and having an error rate of 4%. As an additional note, 2016's winner had an error rate of 3% and 2017's of 2.25%. Had it not been for AlexNet in 2012, the error rate may have lingered around 20% for another few years. This because while most machine learning algorithms that have been in use for decades work great for smaller structured datasets, when it comes to more real-world datasets, large and unstructured, the performance of machine learning algorithms falls drastically. Deep learning acts like a turbocharger of sorts for machine learning algorithms. As stated earlier, instead of manual feature extraction, the neural network acquires its own internal representations of the data, that being the relevant features that describe it. To add to this, these networks can be trained in an unsupervised or supervised manner for both unsupervised and supervised tasks. As quoted from the paper discussing this breakthrough in 2012, titled ImageNet Classification with Deep Convolutional Neural Networks, our results show that a large deep convolutional neural network is capable of achieving record-breaking results on a highly challenging dataset using purely supervised learning. To simplify our experiments, we did not use any unsupervised pre-training, even though we expect that it will help, especially if we obtain enough computational power to significantly increase the size of the network without obtaining a corresponding increase in the amount of labeled data. Our results have improved as we have made our network larger and trained it longer. So to reiterate, the AlexNet victory in 2012 was a neural net trained in a supervised manner, executing on an unsupervised dataset. As I'm sure is clear now, these networks and the results they produce translated in nearly every task machine learning algorithms tackled beyond just image recognition. Neural nets in principle have existed for decades, as we saw in the Birth of AI video, so why their sudden rise in effectiveness and popularity now? Well, as we discussed in the last video in this series on machine learning, some major factors include the pervasiveness of big data and increases in computing storage and power. Other major factors include increasingly parallelizable applications, streamlined software interfaces like TensorFlow, the list can go on and on. As stated earlier, conventional machine learning techniques were limited in their ability to process natural data in its raw form, whereas deep learning benefits from vast amounts of training data to produce its models. In other words, deep learning is able to leverage big data. Also, deep learning, unlike traditional machine learning, excels at processing unstructured data, as a network's underlying structure derives the representations and features of the dataset. Additionally, the composition of the networks, that being the mathematics these neural nets operate on, matrix operations, benefit greatly from parallel operation, and therefore increase the computing performance. While this is a lot of terminology all at once, I promise this will all make more sense by the end of this deep learning series, after we discuss the structure of neural nets and how they work. Coming back on topic, as I hope you can see now, deep learning really is a culmination of advances in many fields and the hard work and dedication of various groups and individuals. When most people in the mainstream say AI nowadays, or when businesses use the term to hype a product, they are really referring to machine learning, and when they say machine learning, they really mean deep learning. Just like Matryoshka dolls, they are further subsets of one another. As I hope you took away from our machine learning series, machine learning at a high level is essentially pattern recognition, a subset of intelligence. Deep learning then is turbocharged pattern recognition. Over the past videos, we have seen the field of connectionism evolve from the singular perceptron nets of the 60s to the shallow multilayer networks of the 80s and many other innovations, leading to the development of modern deep networks with tens to hundreds of layers, each building layers of representation and abstraction on top of one another. Now, while it may take a lot of work to build a deep learning system, as we'll see in the next videos in this series, if you want to learn more about deep learning, and I mean really learn about the field, from how these artificial learning algorithms were inspired from the brain, to their foundational building blocks, the perceptron, scaling up to multilayer networks, different types of networks such as convolutional networks and recurrent networks, and much more, then Brilliant.org is a place for you to go. Now, what we love about how the topics in these courses are presented is that first an intuitive explanation is given, and then you are taken through related problems. If you get a problem wrong, you can see an explanation for where you went wrong and how to rectify that flaw. In a world where automation through algorithms will increasingly replace more jobs, it is up to us as individuals to keep our brains sharp and think of creative solutions to multidisciplinary problems. To support futurology and learn more about Brilliant, go to brilliant.org/futurology and sign up for free. Additionally, the first 200 people that go to that link will get 20% off their annual premium subscription. At this point, the video has concluded. We'd like to thank you for taking the time to watch it. If you enjoyed it, consider supporting us on Patreon or YouTube membership to keep this brand growing. And if you have any topic suggestions, please leave them in the comments below. Consider subscribing for more content and check out our website and parent company EarthOne for more information. This has been Ankur, you've been watching Futurology, and we'll see you again soon.